I want to talk for a second a little bit more specifically about this idea of charge, and I want to contrast it with the idea of mass. You all are very comfortable with the idea of mass. Typically, you can just take a look at something and it's bigger, you know it weighs more. So you compare yourself to me and you say, yeah, he's got a larger mass. You're even very comfortable with the idea of the units used for mass, the units of grams. So when I tell you that I've got some water, you know that it weighs 18 grams per mole. If I tell you I've got a sodium ion, you know it's 23 grams per mole. You know that if it's a DNA, it's lots and lots of grams per mole. When I talk about charge, though, you don't quite have that same sort of comfortableness with it. And it's important that you gain it because it's, in fact, the charge that's going to allow us to do an awful lot of the work that we want to talk about, because by knowing what the charge is, I can talk about some sort of potential difference that's established in a couple of electrodes here, and I can put a particular charge species, like a sodium ion here, and I can talk about what that charge is going to do as it moves across this potential difference right here. That positive sign up there is a measure of the amount of charge, and the amount of charge is specifically measured as something called a coulomb. And mathematically, we've already talked about what a coulomb is. It was this value on a per charge basis of about 1.6 times 10 to the minus 19 coulombs found in every particle. So whether it was an electron with a single charge, it was 1.6 times 10 to the minus 19. Whether it was a proton, it had that single charge, 1.6 times 10 to the minus 19. A sodium ion with a single charge, 1.6 times 10 to the minus 19. That's the total amount of charge that it had. Now, as a context for you to understand this, it may seem more foreign to you with such a small number, but really, if I talked about mass in grams, and I'm looking at things on a per atom basis, and I decided to take, for example, a gram per mole and divide it by 6 times 10 to the minus 23, by 6 times 10 to the 23, then I end up with a mass per atom that, what is that? That's some number down on the 10 to the minus 24 gram basis. You don't have any particular comfort with that, I wouldn't think, any more than you'd have comfort with the idea of a number on the 10 to the minus 19 basis. The important thing, though, to appreciate is that this is a value here that defines for us this ability to have work happen as you move across a potential barrier because of that charge. Now, I can go ahead and put that on a per mole basis in the same way that I can with grams, so that if I decide to put this on a per mole basis, I have to multiply times 6 times 10 to the 23rd particles, and then I would have a value which is the number of coulombs in a mole, and that would be 1.96 times 10 to the minus 19 times 6 times 10 to the 23rd, and that would be equal to a value of about 9.6 times 10 to the 4th coulombs in a mole. So in the same way, there's 18 grams in a mole for water, or 23 grams in a mole for sodium. There are 9.6 times 10 to the 4th coulombs in a mole for a single charge. Now, that might to you seem like a foreign number. The nice thing about that foreign number, though, is that it's the same no matter what kinds of charge you have. So a proton, an electron, and a sodium ion all have 9.6 times 10 to the 4th coulombs in a mole. We give a special name to a mole of charge, and that special name is the Faraday. And it's named after the guy who's identified as the father of modern electrochemistry. So when I talk about having a Faraday of charge, I'm talking about having about 9 times 10 to the 4th coulombs of charge available to me in a mole of material.